Object of today is to learn all of the rules of differentiation, including the product rule and trigonometric functions. So rules of differentiation. And we start with first reviewing the limit definition of the derivative. So let's say that I want to take the derivative of number 7, let's say. So what would be the way to do this? Well, we would have to compute the limit as h goes to 0 of f of x plus h minus f of x divided by h. But in this case, function is 7 at all times. So what you would get is you would get a 0 in the numerator because it will be 7 minus 7. So the answer would be 0. If we try to do the derivative of x, we would say limit h goes to 0 of x plus h minus x divided by h. So these x's cancel, and then h's will cancel in a second sweep, and we would get the answer is 1. If we try to do the derivative of x squared, we would have the limit h goes to 0 of x plus h squared minus x squared divided by h, and this is the one where we actually do the work. So we have the limit h goes to 0, and you have x squared plus 2xh plus h squared minus x squared over h, and then these x squares cancel, and we end up having, factor out h, 2x plus h over h, so now h cancels, and we have h goes to 0, we just have 2x. No matter, and we did a whole bunch of these when we did 3.1, before we were looking for the tangent lines. So that's that procedure. This can be done for any function. And you see that as the functions become more involved, the calculation becomes more involved. So by doing this over and over and over and over again, people started spotting patterns. And then today, when we are taking the derivatives, well, today we just fire up Mathematica and do it, which I hope you already installed. Yeah, in 2 cases. The rest of you are too busy.
It's way different than Wolfram though. Like you have to know how to enter this approach is this. No?
Nope, nothing. Just words.
Then not.
We'll talk about it. So, what are these rules? What are these rules? The first rule that we are going to memorize is that the derivative of a constant is 0. No matter what that number is, it's going to be 0. So 1 and negative pi and 10/3, all of those, the derivative is immediately 0. Maybe I'm going to do these rules in red. So the derivative of a constant is 0. The next piece is that the derivative of x to some exponent n is n x to the n minus 1. So what would be examples for something like this? Let's do 3. Well, definitely we started with the derivative of x squared. We just did that. Was 2x. Why? We take this exponent that was 2, which was n, you bring it in front, and then exponent 2 was reduced by 1, so 2 minus 1 is 1, and you just get 2x. If you have a negative exponent, let's say x to the negative 8, then negative 8 drops down, and then x to the minus 8 minus 1 is minus 9. And you can also use this for any type of radicals. So let's say you have a of x. Now, that is the same as asking what is the derivative of x to the 1/2, because that's the exponent, right? So you can use the same rule. You drop 1/2 in front and then x to the minus 1/2, because 1/2 minus 1 is negative 1/2. All of these are examples for this rule, and as you can see, it covers a whole wide range of these rules. Yes? That would be covered under section with the chain rule, because that is composition of functions. If you put a function different than x within the square root, right? So we'll have a separate rule for that. And the answer to what you said is yes. By the way, the answer is yes, but it will be covered in a different lecture. So I will not be addressing it now. But yeah, we're going to get there. So we covered constants. We covered x to the n, where n can be positive, negative, or a fraction to accommodate all of the square roots, cube roots, and so on. Another one that we need to memorize is that the derivative of e to the x is e to the x. That one stays unchanged. It is the only function in the galaxy that does that. So the derivative of e to the x is x. The derivative of ln x is 1 over x. And before I get into these rules, I just want to see if they put anything else in here. Nope. So that would be it in terms of the differentiation rules. And now we're going to take a look at the properties so that we can use these. So now, properties. First property is that the derivative of c times f of x, which means that if you are multiplying a function by some constant c, that c can be kicked out all the way in front of the derivative, and you just focus yourself on taking the derivative of the function. Immediately an example for this. Let's say you have the derivative of 10 times x to the minus 4. Well, this is the same as 10 times the derivative of x to the minus 4. Rule for differentiation to deal with that function part, and we just copy the 10. So this is going to be negative 4 and then x to the negative 5, because you are subtracting 1, for the final answer of negative 40 over x to the 5. If you want to make it nice, right? You put negative 40 over x to the 5, because negative exponents will push the x in the denominator. So this was an example, and the only thing that we are focusing on here is that this constant gets to drop in front, and that's exactly what happened with 10. 10 was pushed in front of the derivative, and we did the derivative, applied it only on a function. And the next one, so that's that rule. Then we have a sum and a difference rule. I push that into one. So sum and difference rule says that if you have a derivative, if you have the derivative of two functions, you can do derivatives separately and add those results. Now this is a big rule, very important rule, because this allows us to actually take derivatives of more complicated functions, and we take that term-wise. So each term is its own problem. And if you have a minus, there will just be a minus over there. So those are the three rules written into two formulas, right? You have the constant multiple rule, you have the sum and difference rule, and that's it. So let's take a break from all of these definitions and rules and just work out a few exercises, and then we'll define the higher order derivatives, second derivative, third derivative, and so on. And we're done with 3.3. So you must memorize these four rules. Actually, I should chisel these onto the board. So that you can use them now. One more time. The derivative of a constant is 0. Derivative of any kind of polynomial term is going to be x to the n minus 1, but this one also includes square roots, cube roots, and all of those radicals, because n could be a fraction as well. Then d dx of e to the x is itself e to the x. d dx of ln x is 1 over x. So those are the basic rules. And now we have the property that c times f of x is c times the derivative of f of x. So what this does is it's going to kick the constant outside. And we also have the sum slash difference rule, where you have f plus g or f minus g, and that's going to be the derivative of f plus or minus the derivative of g. So I listed 7 things over there. These 2 things are under here. And that takes care of this portion for us. So now let's take a look at exercises and see which rules are used where. As I said before, guys, you can just use the limit definition all the time. You don't have to learn these shortcuts. Right? No, you're going to learn the shortcuts, obviously. You don't want to crank that limit all the time. So let's take a look at example that says, what is the derivative of 3 square root of x plus x cubed? So we are going to use 4 different rules here. It looks easy, right? You just do it. But technically, it's 4 different rules. 4. The first rule is going to split this into 2 separate derivatives, because we are allowed to take derivatives each term independently. So all of the pluses and minuses immediately break up the derivatives. Now the first one will kick 3 out. That's the constant rule. And you are just focusing on taking the derivative of x to the 1/2. The second one you just do as 3x squared. You're done. So that's the power rule. So we did the sum rule, then we did the constant rule, and now we're going to do the 2 power rules. So now this is 3 times 1/2 x to the negative 1/2 plus 3x squared. And when you do this, you get 3/2. You can put the square root of x downstairs plus 3x squared. And that would be the answer. That is the derivative. Now clearly, within 2-3 days, you will be going from here directly there without writing anything in between, because you will know that you can take derivatives independently. You know that there are 3 copies down. So you'll be technically focusing your brain power on figuring out the derivative of square root of x. That's where your focus will be. The rest will automatically just be rewritten or broken into pieces and so on. Yes?
I'm a little bit confused since the rule says that the derivative of a constant equals 0. When you pull 3 out, how come you're multiplying the derivative of x to the 1/2 by 3 instead of 0?
But see, the derivative is no longer applied to the 3. Over here, derivative is applied to 3.
Right.
And once we kick it out, because of the rule that we have, the 3 is now in front of the derivative. Derivative applies to what comes after it, not what is in front. So that 3 remains as.
So once you use the power rule, the 3 becomes in front of taking the derivative of x to 1/2.
Yeah, once it comes out, that's it. It's no longer under the derivative, and derivative will have no impact on it. So it remains 3.
Okay.
Next example, let's take a look at the derivative of 5e to the x minus 7. So what do we get? 5e to the x is correct. So derivative of e to the x is e to the x. You have a 5 that multiplies it, that copies. And derivative of negative 7, which is the derivative of constant, is 0. So that just dies off, and the problem is solved. That's it. I hope you're not disappointed.
When is it equal 1? When it's about x, right?
Just x, yes. So let's pull some of the examples from the textbook. See what you guys can expect on the homework. Let's talk notation real quick. So if you have a function like this, and it says it's, I don't know, 3x squared plus 2x minus 1, and they ask what's the derivative, in this case you have to start a new line. We talked about that last time. So you have to go and you say f prime of x is equal to 6x plus 2. It is the exponent will drop down, so 3 times 2 is 6, x, 2 minus 1 is 1, so x to the 1, and then plus x is going to, derivative of x over there is in the middle term is 1, so 2 times 1 is 2, and then derivative of negative 1, which is constant, is 0. Yes?
Possibly later on one line saying f of
Yes, but that's going to be in chapter 5. All the way. We'll come back to that. So I'm going to say this. So this is one whole unit. Or I can say the derivative of 3x squared plus 2x minus 1 is equal to 6x plus 2. And that's another way of noting the same thing. So please observe and understand over here that you cannot put equal sign in front of, in between the derivative and the function, because they're not equal. This and this is not the same. So you cannot put equal between them. If you have f of x equals to some function, then you have to start a new line saying the derivative is that. Now, why is this possible? Second notation. Second notation is possible because you have derivative on both sides. On the left-hand side, you have derivative of this is that. They're both derivatives. Both sides are derivatives. The advantage of this is less writing, less space, and I hope better understanding. Because it says the derivative, there's a multiplication there, of this is that. So that is the only way how you can write your derivative and a function in line, combining them with connecting them with the equal sign. So you say derivative of the function is this function here. So that's why this is possible. So you just need to be a little bit careful about that. Now, we can also we can also use different variables. You will find a lot of times you will use, instead of x, you will use t. T stands for time. Also in physics it's used a lot. So, and engineering obviously. So let's take a look. Any of these problems. So s of t is 4 square root of t plus 1/4 t to the 4th plus t plus 1. So what is the derivative? Well, s prime of t is equal to what?
Like t and the addition signs next to each other.
What happened?
T next to a plus sign is like, you know what I mean? I feel like it would be a lot easier with just a different variable.
There you go. You know what? It reminded me of the best passwords in the world. What you just said. Yeah. If anyone asks you to create them an email or something, and just create the password for them, so they don't have to worry about it. Just create the password of ones, capital I's, lowercase L's, uppercase O's, and zeros. It's awesome.
If someone sees it,
Yeah. It looks like this. Perfect. A password like that. It is clearly lowercase l, capital I, 0, O, lowercase l, capital I, right? You get the idea. So yeah, you'll have to deal with t's and pluses because we don't have a, that's how we write t for time. So you'll have to get used to it. All right, so we have 4 times 1/2 t to the negative 1/2 because square root of t is t to the 1/2. Plus we copy 1/4 and then we have 4t cubed and then plus 1 and then I'll say plus 0 because the derivative of plus 1 at the end is 0. And now we just simplify this to 4 and 2 will cancel. So we get 2 over square root of t. 4's cancel, so plus t cubed, and then plus 1. And that will be the answer. and the most simplified form. Now, how would you differentiate this? How would you go about differentiating this one? Very good. You have to FOIL it first. We are going to have a special rule called the product rule for multiplication of two functions. In this case, we can cheat and we can FOIL. So that is, as of right now, the only way we can solve this problem. So we have 6x cubed plus 4x plus 3x squared plus 2. And the derivative would be 18x squared plus 4 plus 6x, and then the other one is 0. And then you sort it in the descending order, right? So 18x squared plus 6x plus 4. And that takes care of it. So the last concept for 3.3 is high. Do you want one more example? Yes or no?
Nah, good.
All right. Higher order derivatives. So whereas the first derivative, there should be a second derivative and a third derivative and a fourth derivative and a fifth derivative and so on. Where you can have higher order derivatives. We experience that in the nature. When you have a position function, which is the graph that it's on the floor, that you in a car or ant is going to travel on, that path is given, and then you can take the derivative of that, it will be velocity, you can take another derivative of that, see that's already higher derivative, second derivative is acceleration, and then third derivative is called jerk, that's the third derivative, and then there's no fourth after that. So that's for this particular application. So higher order derivatives are going to be second, third, fourth, fifth, and then as high as you need to go or want to go to take derivatives. Usually in application, 3 or 4 derivatives are the most. We're not usually. It is. That's what it is. We don't go any higher than those. But theoretically, in mathematics, you can go as high with these derivatives as you want. Now the trick is that in order to find, let's say, 7th derivative, what you need to do is to take the first derivative of the 6th derivative. So you have to have all of the derivatives up to that point, and then you take the next derivative. So technically what you're doing is you are taking the first derivative all the time, keeping track where you are. In our previous problem, as you can see, I can take now another derivative. Another derivative will be 36x plus 6, and that will be second derivative. And then another derivative of that would just be 36. Then the next one would be 0, and then all others forever and ever and ever would be 0. That goes for polynomials, because they eventually die off, because they have the number at the end, and then that's 0, and then that's 0, and so on. But you are going to have functions that will never die off as you take these derivatives over and over and over again. Think of e to the x. Right? E to the x is always e to the x. You can take the derivative there 5,000 times, you're still going to be at e to the x. Sines and cosines will be periodic and cyclic. So they're going to go back between sine and cosine forever. and think of the ln x. It goes 1 over x, and then 1 over x squared, and then 1 over x cubed, and so on. So that one will also never go to 0. Polynomials go to 0, but not the other one. So higher order derivatives are going to be the derivatives that are taken after you take the first derivative. So second, third, and so on. I will write higher order derivatives as f double prime of x, f triple prime of x, f, and then now we switch the notation to the fourth, and then let's put little n up there, meaning the nth order of the derivative. Let's say you need 17 derivatives for whatever reason. You're showing off, technically. Now, equivalent notations for Leibniz would be d squared f over dx squared, d cube f over dx cubed. You can use f or y, whatever. d to the fourth f over dx to the fourth, dn f over dx to the n. So these are the equivalent notations using Leibniz notation. And as long as you are remembering that higher order derivatives, all you need to do is you just keep taking first derivative off of your previous answer. That's all you need. So let's take a look. If I start with f of x is equal to 8x cubed plus 3x minus 9. The first derivative, which is f prime of x, also noted as dy dx, let's say. So the derivative would be 24x squared plus 3. The derivative of negative 9 is 0. And now the second derivative, which is d squared y over dx everything squared, is going to be, well, we don't use the parentheses there, it's just dx squared, would be 48x. The third derivative, which is d cubed y over dx cubed, is just 48. The fourth derivative, remember now we're switching notation, is d4 y over dx 4, which is 0. And I'll put here in parentheses all other are 0 as well. So if you go to the 30th derivative, it's just going to be 0. Now remember what I said, e to the x, ln x, trig functions, they're not going to experience this behavior that when you maybe you take 7 derivatives and then it goes away. They never go away. Yes?
Is there ever a scenario, like a set of numbers in a function that you just can't take the derivative of it?
No. You can always take the derivative of a function. Integration is going to be a completely different story. We do have functions that are not differentiable at the point, but then that's just at a point. They're differentiable elsewhere. So I'll take 1 over x. 1 over x has a vertical asymptote at 0, right? That is where the parts of the function go to infinity. But when you take the derivative, last lecture, yesterday, the derivative will have the vertical asymptote and the same crazy behavior at the same spot. So that's why you can take the derivative of the function, because the madness, call it that way, is contained in the same spot. So if you let's take a look, since you asked, f of x equals 1 over x, and the associated graph is this, and we know that there is a vertical asymptote at y-axis, which is x equals to 0. Now, what is the derivative of 1 over x? Well, that's x to the minus 1, drop down minus 1, and then x to the minus 1 is x to the minus 2, so x squared downstairs. So how does that look like? That's going to look like this. Now you still can see that vertical asymptote at 0. That cannot change using the derivatives. Let's do one more derivative because we can and because we care. That's minus 1 times 2 negative, so it's positive 2 over x cubed. Now we're going to cheat on this graph. The ways of solving this in graphing it without the calculator, you can always do middle school method, which is compute few points and connect the lines. Or just do what I'm going to do, which is I'm going to use Mathematica since you had the question. And I will show how you get to use it the same way as Wolfram Alpha. So once you guys download Mathematica, which the email was sent to you yesterday, you will create the free account. So when you click on that link that was provided, you will create the free account. So go to the bottom one. There are 3 buttons there, so click on the bottom one. Create the account using RVCC email. And then once you have the account, they will email you. You will be able to log in and go in and download the software. It's about 2.5 gigs. So it could take anywhere from 10 to 30 minutes to an hour, depending on your internet connection. Once you have that downloaded, you will be given a key, which I believe it's emailed to you. That's why you have.
Goes into spam though.
What happened?
The email that they for the key goes into spam though. So
Well, yeah, it depends on how much you spam other things.
Okay.
So yeah, but okay, look at the spam as well. Thank you. So you get the key, you register. Once you install the software and you run it, this is what you get. And you need to click on the new document. It will list the old stuff that you did prior, but you can just click a new document there. And once you're in there, it looks intimidating because it's like, whoa, what now? It's like nothing there, right? But there is this little plus over here where you click on Wolfram Alpha query, and that's where you start working. So once you open this plus, this dialog comes up, and you have these options here. The first option on top is the Wolfram Alpha code. If you want to unleash the ultimate power of this software and actually learn how to use it for industry and everything, that is what you have to learn. Countless YouTube videos, and you have under help and examples and so on. It's a programming language. If you learn Java and you learn whatever else, you will have no issues learning that one. It's not a big deal. These are the 2 that are Wolfram Alpha Lite, where you get to talk to the computer in a language that you would speak regularly. So what do? First one is free form input. Free form input, if you click on that one, it will use local resources. It will use the software that is installed on your computer. It will use the processor of your computer to compute stuff. And you do not have to be connected to the internet to do work. And the third one over here, Wolfram Alpha query, is the one that only works if you're connected to internet because you are using their cloud computing. So the same statement that you would type here, you get to type here. Doesn't matter. You will spell it out. Differentiate x squared. That's you literally spell it out the way you would say it. You type it in and you push enter. Both of these will give you the same answer. But as I said, the last one over here has more detailed answers, but you have to be connected to the internet. So, right, Desert Island, this is the one you use, right? You wouldn't leave without your laptop with Mathematica on it, I hope. Yeah. I have nothing to do with this. It is the automated. Yeah, all I did is I gave the link. I gave the link. And but you have to resolve that stuff. Registration, everything else.
I mean, I think you register on.
Yeah.
You don't know if I'm all you're all
Yeah.
about them.
Yes.
If we're trying to sign into our email, do we do that from the website or from like Google?
Signing into the RV email is from the main website. So you can just go to trying to get. So once you can Google RVCC, you will get this website and RVCC login. Eventually, I think they are going to have the email shortcut there as well. So when you log in here, there is a link for email, which you have to log in into again with the same credentials. So G number and RV password, you can change RV password into anything. You type them here, and that brings you in. Once you're in, you click on email, and you log in with the same stuff. So,
It's under Office.
yeah. Right here. Click here to access Office 365 Outlook web access. That's where the email is. And that's what it is.
I wonder if they're going to update that whole format. The lines then.
Yes.
They're going to update all that.
That's going to be changed as well. Maybe even during the fall semester, but most likely spring. So soon. All right, so what do I want to do to end that problem? I'm going to go to Wolfram Alpha query because I'm connected online, and I'm going to say graph because we are working on that problem. 2 over x cubed. 2 divided by x caret 3 and hit enter. So now it interprets the fraction first and it gives you the graph. So it looks almost as the first one, and you see that asymptote at x equals 0 is preserved everywhere. E to the x is always e to the x, so the 137th derivative of e to the x is e to the x. Okay. Well, we're done with this. That's 3.3 with basic rules. They're listed on the board. For the higher order derivatives, you just keep taking derivatives from the previous step. And the next section is the one that deals with the product rule and the quotient rule. Is it a good time for a break? Yeah? All right. Take 5. I will restart the stream once we are back.